I love synthetic mathematics so much that I'm working towards a synthetic mathematics of synthetic mathematics. And that's what this talk will somehow be about. I put in, the official title doesn't have the infinity because the work that we have checked and proved things about are about synthetic locale theory. But I'll say in the motivation that actually we would like to go higher. So if you think of a topos as a, if a locale is a one locale, then a topos must be a two locale. But an infinity topos is the same as an infinity locale. Okay, and this is a joint work with my students, Johannes Schip van Branitz and Mark de Mounier Williams. Okay, so the motivation is that we have a proliferation of settings for synthetic mathematics. And we have seen some of them already. So we've seen synthetic algebraic geometry, where you work in the sheaves over the so the classifying topos for K algebra. So you do something like pre-sheaves on K algebra up, and there you have a universal ring, and you can maybe put in a sheaf topology on this and make the local ring and so on. So we've heard about this. This is great stuff. There are also some earlier developments in synthetic differential geometry, where you could pick some well-adapted model. So this could be something like the Dubuc topos, which is somehow related to this a little bit. It's sheaves on C infinity rings, which are germ determined of finite presentation or something like that. Or maybe it's the Caillet topos, which is sheaves on another side of kind of C infinity rings, but of a more particular shape. So Cartesian spaces, so C infinity of Rn tensored with a Weil algebra. So you add some formal nilpotence, and then you also get to do some differential geometry with nilpotence. Like you have the nilpotence here, which allow you to talk about tangents and cotangents in algebraic geometry. But there are, of course, many others. Let's see, what do we have? Well, we heard today about synthetic probability theory. And I won't recall here what the topos construction was. It was an iterated extension. And then there are various kinds of topological notions. So the whole range of settings for synthetic topology so you can do something like sheaves on Euclidean topological spaces. So these were like, so Rn and continuous maps, collection of them. Or you could do something like some other small collection of topological spaces, maybe Cantor space, 2 to the n, or n infinity, or so a generic convergent sequence, and there are many others. Okay. And something that I've also been working a lot on, which we'll hear from Jonathan in a little bit, is about synthetic category theory, where the setting is somehow pre-sheaves on the simplex category, or, which is quite useful, pre-sheaves on a slightly larger, something that gives a larger topos, pre-sheaves in some kind of cubical sets, or even pre-sheaves a bit larger. Again, you can take distributive lattices up of finite presentation. So then that begins to look like topology. Okay. So we have all of these settings, but what if you want to do synthetic derived algebraic geometry? Maybe you would like to develop some higher algebra using the synthetic category theory, and then therein define a notion of what it means to be a higher ring, and then you want to look at a classifying topos for a higher ring, or maybe you want to combine others of these. So there's been some work by David Myers and collaborators on combining the simplicial type theory with something like the Caillier topos, or setting for differential geometry in order to do differential cohomology theory. So there are many ways you could think about. You may want to move between these different settings, relativize them to one another, and then because you want to reap the benefits of working synthetically, you don't want to just work inside your favorite setting in the internal language. You also want to cache out at some point and say, oh, externalize now and give me the cache value of my internal theorem. So for instance, maybe you prove something in synthetic differential geometry, and at the end of the day, you want to conclude something about smooth manifolds in the world you started at. Okay. Yes, the word synthetic. Right. I think I'm not a professional philosopher anymore.
No, but as a mathematician, if you remember the original.
Right. So I think you could argue that the original meaning of this would be doing geometry, plane geometry in the style of Euclid. So you postulate that you have some points and lines, but you don't say that the lines are sets of points or something like that, or the circles are sets of points, but they are primitive objects, and you axiomatize how they relate what are the relations between the points and the lines, and the circles and the lines, and so on. Right. Okay. And there's something similar in the synthetic category theory. It's not quite synthetic. Not every type is a category, but we have some propositions on types that make them categories, so they're not very analytically. They're -1 analytically constructed from things. And the same thing in some of the other settings. Not every type is going to be an affine scheme, but it's proposition on a type to be an affine scheme. So you don't have to do a lot of analysis. You don't have to, if you do things fully analytically, you start with some notion just of bare type or set, and then you fully analytically build up all the objects you're interested in terms of fundamental structures. And that, of course, gives you the full power of control, because you know exactly how things are built up, but you have a lot of proof work to do. And this is, again, where I maybe borrow Alex's apology, or that this is somehow connected to efficient proofs, if not as efficient proof systems, to work synthetically. Right. Tomorrow we'll also hear about synthetic stone duality, which actually I'll come back to in a little bit. Okay. Right. So for a long time, I think it was more of an art than a science of figuring out what are the properties you get from working in these models, particularly if they are constructed as the classifying topos for some theory. What properties of the generic model hold in its classifying topos that are not true for any model anywhere. And this is where Ingo had a brilliant idea, and I'm going to give you a reinterpretation of this following a blog post by David Myers. So this is called quasi-coherent induction. And so I didn't write this down, but the goal of this line of work, which I had been thinking about for a while, and it turns out that David Myers and others have also been thinking about for a while, is how can we make a synthetic language. So maybe I should put this somehow. So I'll put this up here. So the goal for this line of work is, well, we like doing synthetic mathematics, but it's quite analytical work to move between all the settings of synthetic mathematics. So it would be great to have a synthetic mathematics for synthetic mathematics. Okay, and quasi-coherent induction is probably going to be one ingredient of this, and so the hope is that there's a kind of type theory where this would be a principle of computation, and I'll tell you what David's imagined version is. It's something like the following. So you have a base topos B, where you start. Then you define E, let's say it's some setting where you want to work. And then you look at, let's say E is B together, classifying some theory T. Then you can look at another topos, E arrow, so the arrow topos of E, classifying two objects that E classifies together with a map between them. So this would be somehow B extended with the theory of a T homomorphism. So two T algebras and a T homomorphism between them. And then you can take the domain of your morphism, and that's giving you a T object up here. Because here you have two T objects and a map, so there's a classifying map down here. And then you also have over this, you have E itself with the diagonal embedding. Let's call this I. So this classifies, given we have the universal model up here, and there's the identity map out of the universal model, and this gives you a map into the pairs of algebras and a homomorphism. Okay, so now the idea is, so let's put another copy of the arrow topos here and a topos over the arrow topos. And let's say we have some topos X classifying something and a classifying map X from E to X. And this maybe is called P. Then under the certain condition that P itself is quasi-coherent, which I'll come back to in just a minute. So there's a condition you need on how you define X over the arrow topos. Then you get a lift. And what you should think about is that this looks like path induction. So path induction says, I have a type, and I have the type of paths in A. So if you're doing cubical type theory, you really have an interval object and something like this. And if you have a type family over the paths in A, so some type family depending on two elements of A and a path between them, and you have something that sits over reflexivity, so a lift like this. So this says that you have a lift over the constant path. Then you get something for every, you get a section of P. Okay? So this is what you should think about. This is analogous to path induction. And now I should tell you what this condition of quasi-coherence is. And I will refer you to the blog post on the Topos Institute for more details. But basically it means that X is defined relative to B with locally, so it's locally of constant small presentation. So now we run into some issues we heard about yesterday as well from Benno's talk about that we need a good constructive theory of regular cardinals, and regular cardinals are not stable under reindexing. So there's definitely some work to be done to make all of this precise. But in this approximation that I will tell you about later, this happily doesn't cause any problems. Right. So what can you do with the quasi-coherent induction principle? Well, you can do the following. You can let x be the pullback along D of the object classifier over E. This says that now X classifies an object in E. So this is the same thing as X is a sheaf over E. And here we have the arrow topos again. Arrow topos. So if this was quasi-coherent, then any object in E is quasi-coherently definable relative to this slice. So the theory, so what you're doing when you're pulling back along D is you're getting the theory of a T algebra out of the universal model. And likewise, you can do the same thing. So you get, what should we say? Every object, every X in the sheaves on E is definable from this theory. So the universal T model sliced over, let's see, the pullback along the domain. Along this classifying map. There's a map. Let's call that the global thing G star of T. So this is why this quasi-coherence notion comes in. So Ingo explains quite lucidly why you need something like this, and David's blog post also has details on how this comes in. Okay. So I'm not quite yet done with the vision that we want, or that both I and David and Mitchell Riley have been thinking about. But now I think David and Mitchell give a more concrete wish. So David and Mitchell propose something like this, and it's following Owen Lynch, also at the Topos Institute. So this is called element model type theory, and you'll see why in a little bit, because the ingredients are as follows. So you have, just like in ordinary type theory, you have a judgment of types and a representable map of elements. So if you have a type, you can extend your context by an element of that type, and if you have a type, you know there's a judgment of being an element of that type. And you have another representable map of theories and models of a theory, and there's a classifying map of those. And it should be possible to take from a type, give a theory of its elements. So they write this with a bold EL, and then you get, they want a pullback square like this. And the other ingredient they want in their EMTT is a particular theory of types. So a map like this. So type itself should arise like this. The universe of types should be the models of the theory tie. Okay. Okay. Then there are a bunch of other conditions. But let me tell you about the intended semantics. So the intended semantics is, as I indicated that we wanted to do, we wanted to study all toposes together. So the intended semantics has contexts, toposes, and the types of the types over E are the sheaves in E, and the theories over E are the slice. So all toposes over E. And this is also, so I should mention that there's a bunch of preliminary work in this direction. So Steve Vickers, who's long been an advocate of the connection between topology and logic, calls these elephant theories because they're very large. And they're, of course, related to Johnston's The Elephant. Okay. And the map maps a sheaf over E is the same thing as an étale map, étale geometric morphism to E. So if you take an A here is mapped to an étale, let's call this E. E dot A is going to be somehow an étale geometric map. So the sheaves on E extended by A is just the slice. So it's a sheaf on E with a map down to A. Okay. So that's the intended semantics. And then we want something a bit more than that. And this is where usual type theory comes up short, because we also would like to have a map or a family of maps from theories. Every theory should give a type of the models of that theory. However, this is not stable under reindexing along all geometric morphisms. It's only stable under reindexing along the étale geometric morphisms. So what they want is somehow a picture like this. So we take these maps and restrict them to the subcategory of toposes and étale maps. And then we're going to write it like this. So we have theory, but restricted to use like an ampersand. We have the models, restricted, elements, restricted, types, restricted. And then there should be somehow this map M that takes a theory and gives you the type of its models. And this should make this a pullback, where restricting to this means restricts to toposes with étale maps. By necessity, this would give you a way of talking about the constructions on types that are not stable under all morphisms. So you can add in up on this board where there's no restriction, you can add that these universes have sigma types and terminal objects and so on. Maybe I'll put this in here. So you want 1 and sigma and identity, I think. You could put in some finitary inductive types. But basically geometric constructions. But what if we know that the types in a model, types of the sheaves over a topos, they are closed under all type formats. They have universes and pi types. And how are we going to get them? We're going to apply these model functors. So we're going to go up into theory and apply this mod. And then we can, so that we, let's say oh, yeah, there's one more thing I didn't say. Let me just put it in here. So we assume plus pi types for, so we have pi of theories over types. I hope that makes sense. So if you have a type and a family of theories indexed by that type, then the pi type should again be a theory. Then if you get a theory, you apply the model construction, you get a new type. But a type is not stable under all reindexings. Okay. So this is a bit of a non-standard type theory, so hopefully one day something like this could be made to work. So that's one issue that made me want to do something slightly different than what they're doing. The other is that here I have been silent about size issues. And of course, there's a lot of size issues. This whole setup is very large, and it's also the case that, well, you need to have like maybe you have theories for every universe level. So you have something like this, and you have some j. But how large is, well, actually you get to choose. You get to choose for every j bigger than I to take the models of size j. So for instance, let's say I is 0, and you define the classifier for a ring. Then for every universe level, you get the models of the theory of rings up to universe level j. And that's going to be, I guess, j plus 1 here, just to be on the safe side. Yeah?
Sorry, can we slow down a little bit?
Yeah?
If you say the lower thing is the intended semantics of the upper thing,
Yeah.
can I think about the upper diagrams as living in stacks over the two categories of toposes?
Yes, yes. Yeah, that's
the idea. Okay.
yes.
And then
Maybe, I think that should work. I think that maybe somehow it should also work because you don't have a standard type theory. Maybe it should just work in just pre-stacks over the two categories. Maybe you don't need to take into account, but what I will do in a little bit, we'll take into account the natural topology on the two category locales. Okay, any other questions about this? Because then I will go on to, so there are two issues with this. It's a quite non-standard setting. You can't program this in Acta today. And two, there are lots of size issues that are, make the semantics quite difficult because somehow you want to model this in all toposes all at once, but you want to have these stratified hierarchies, and that's not going to mesh very well with usual pre-sheaf semantics or pre-stack semantics.
But the idea is that this is a kind of a representative map category
Yes.
in the sense of Uemura.
Yes, in the sense of Uemura. I should also mention that Uemura have some very nice notes. Yeah, Uemura, Taishi Uemura also have some notes on his webpage towards topos type theory. So this is also related work.
So you wanted to automatize the category of topos with the semantic notation?
Yes, in a useful way. In a useful way so that we can construct theories, construct the sheaves, and work with the sheaf toposes for classified by given theory, and extract externalizations and other things we want to do. Okay, so it's a kind of an ambitious thing, but now let me switch to a, what can we do today without inventing, yes?
You mean Grothendieck toposes?
Yes, yes, I only mean Grothendieck toposes. And I also want to work predicatively and constructively because I want to eventually work with higher things, and therefore it doesn't really help me to having predicativity. It would help for the case of locales, but I want the higher thing anyway, so I might as well work predicatively and face all the problems today rather than suffer tomorrow. Okay? Yeah. Right. Okay. This one. I actually have more board. I mean, you use a different board. Okay, so what can we do today? Let's say I want to have a theory, the synthetic mathematics of synthetic mathematics, that I could axiomatize in Acta today. That's my goal for today's talk, for the rest of the time here. I don't have much left to do. Much time left, so I'll maybe speed up a little bit. Well, so as Jonas was saying, they're like the eventual semantics could be very large, right? So eventually we might want to go to something like infinity 2 toposes because we want to do directed things. Let's forget those. Let's just think about infinity 1. Oh, that's also very hard. Let's cut down maybe to 1 toposes. It's also very hard. Let's cut down to locales. But still work predicatively so that we face the same issues, size issues that we would have at the other levels. Okay. So what we are going to do is use a recipe we can get for getting a model of type theory that knows about this category. So actually, I'm going to dodge one part of the size issue. So I'm not going to talk about all locales. I'm only going to talk about small locales. And because I'm predicative, there might even be large maps between small locales. I'm only going to talk about the small ones. So I'm chickening out of a lot of the problems. So let's define L. So to be U small presented locales and U0 small maps. Okay, and this has a nice small U0 small topology given by the étale covers. Since I'm only looking at locales, it's basically the open covers, but there would make a little bit of a difference higher up in the hierarchy. So then we look at sheaves on L for universes. So U1, U2, U infinity. So you take U infinity size sheaves and you get internal universes U1, so curly U1 up to, so this has universes curly U1 sitting inside curly U2, etc. So this is my universe hierarchy. But what am I going to do about these universes of small presentation? And this is where this idea about the quasi-coherence as being locally of constant small presentation comes in. I actually secretly have a universe U0 that doesn't see anything at all about locales. It comes entirely from the base. So this classifies locally constant small sheaves. Yes, sheaves. Okay. So I'm going to use this U0. I'm going to axiomatize that it could, well, actually for most of the talk, the rest of the talk, it'll just be a cardinal. So a regular cardinal, so have a unit type and closed under sigma. But at the end, it'll be nice to also have it closed under pi, so be kind of the smallest inaccessible that sits below the rest of the hierarchy. Okay, now let us clear a board. Okay, so we have this small universe modeling the locally constant types. We also have some analog of the, so these are in a sense to be thought of as the theories and the models. So if you're defining something in U1, you're giving a predicate on all toposes over your current context. So you're giving an elephant theory. But we also have the universe of elements and types, because that's the representable from the Sierpinski space. So we have S dot, which is just 1 to S, giving this L to tie. Okay, And furthermore, there's going to be a map plus, so here's one size issue that comes in. So S itself, because this category L is not locally small, it's going to come with a map to prop 1. And this map is being equal to 1. So this map picks out 1. Okay, so now what can we say about such a situation? We have an algebra for some theory, so it's going to be something like a U small frame. And there's actually also going to be the free U small frame. You can even put this in, there. You can this will just be prop 0. This is the free U0 small frame. And there's a map, because S is going to be a U0 small frame. It's going to model up this theory, so we have a diagram like this. Okay. And what can you do? So Jonathan will talk later about crisp type theory. So I want to get something on the, I want to put this in. So what do we do for this issue about restricting to a subcategory? Well, if you have enough axioms on S, it doesn't matter that you can restrict not only to just this subcategory, but all the way down to constant, so no variation at all, if you have some control over how things behave with respect to the étale maps anyway. And we're going to get this. So what is crisp type theory? This is a la Mike Schulman's real cohesion, which was actually one of the instances of synthetic mathematics I highlighted in the beginning, where you look at Euclidean topological spaces. So the idea is that you have your topos E, and you have your base B, and you have your global sections map. And that's going to give you, on the level of sheaves, so here are your sets, your category of sets, you're going to have global sections and diagonal, and then you have colimits. And in good cases, this pi, in fact, preserves finite products, and you have, say you have cohesion, and maybe you also have another adjoint here. But for now, we're just going to focus on this part here. So this gives you a modality, delta after gamma, called flat. And so this gives you this, the objects of the sheaves on E, but with no variation. So they're going to be constantly varying. And then we can say, for a crisp affine, so an affine is going to be defined the same way as in synthetic algebraic geometry, as something that is a spectrum of an S algebra. For crisp affine E, for I greater than 0. So if you know something about topos theory or frame theory, you might expect that if S is a frame, and this is the free frame, so and this map is going to be left exact and co-continuous, it might have a left adjoint. Is that right? Right adjoint. It might have an adjoint. Yes. It's going to have a right, might have a right adjoint, but it's not going to have it in this setting here. Also not predicatively, it's not the case that you don't have a very good adjoint functor theorem available. But you do have something if you boost up the sizes. So you can postulate S1. So we have, you might want to have, I should have actually put this in a different way. I realize I'm going to amend this diagram slightly. I'm going to put this down here. So this somehow lives at the level 0, And we're going to have a bigger version of it up here. And then there's a map here, right, so yeah, okay, there's going to be a map there. That's not what I'm really interested in. We had this map here. Is that right? What I had was the equals 1. And yeah, right, so this is going to be, I'm going to say that's going to be not universally such a right adjoint, but there's going to be one after exponentiating with any e. So there's going to be so we can take S1 to the e, take its constantly varying version, take prop 1 to the e, take its constantly varying version, and then you have this, it's going to be the relative right adjoint. That gives you your way of going from a big theory, an elephant theory on E. So here it's going to be this proposition value, so it's just not going to be so interesting yet until we move up to the higher case, but still, nevertheless, that puts you into here, and then we can axiomatize when this is going to be actually small in some cases. Okay, so I wanted to get this down before I run out of time. Okay, I'll come back to this in a little bit. Okay, so now let's clear another board.
I think you have 4 more minutes.
4 more minutes. Okay, very good. I'll wrap up. So there's some freedom in how you define the theory of a U small frame. And we're still exploring what are the best options. So you can think of it as an algebraic theory, so where you have finite meets and U0 small joins that distribute over them. That's not the usual notion of a formal topology or locale. So it may be that there's some other presentations that are more well behaved, but in any case, for sort of formal nonsense, you derive a duality theorem, and so you do have this duality. So you always have an adjunction between set 1 and the S algebra op. Do I have a picture of this? Yeah. So in one direction you take its spectrum. So the spectrum of A is the homomorphisms back to S. And in this direction, let's call it O for observations, left adjoint, where the observations on a set X is just the maps into S. Okay, so this also begins to look a lot like other versions of synthetic topology, like abstract stone duality and what we'll see tomorrow in terms of synthetic stone duality, abstract versus two different versions. Okay, and then you get a lot of. So what you say is that if A is crisp of U0 small presentation, then the evaluation map from A to the observations on the spectrum of A are an equivalence. Okay. And then you get that the exponential a to the s classifies the order in A. So this is going to be the sum of two elements and an inequality between them. Okay, so now you have a way of giving a theory for these, so talking about this theory of these. So you can try to ask the question, which we haven't done yet. So this is now the question. And then I'll wrap up with this. Does this imply quasi-coherent induction? Right, because now it makes sense, because the arrow locale is just the exponential. You have this just as in synthetic category theory. You think of these as kind of object of arrows. I should call this not A, because that's an algebra. I should call it E for the affine corresponding to that algebra. And X is another affine with a quasi-coherent presentation. Do we get this? I don't know yet. We haven't gotten so far. We just checked that we have the duality thing work and that these crisp maps work, so that you can at least try to do some constructions with things. So it's very much work in progress. Thanks so much for your patience. I will show you some references in 1 second.
So could you say more about this vision of constructing synthetic theories more easily? So
right.
In which sense? Could you give an example of this?
Yeah, so in the case of propositional logic, it's a very tight correspondence between usual versions of frame presentations and propositional geometric theories. So there, it doesn't really matter which one you pick, but for, say, for first order geometric logic, it would make a big difference whether you presented your theory of S algebras in terms of sites with a coverage or in terms of this theory itself, and it might be beneficial for ergonomics to present it using the theories, but we haven't gotten so far yet. But hopefully you get an ergonomic system in which you just define a theory, you get the corresponding affine topos, and then you know that maps between affine toposes are the same thing as interpretations of the corresponding theories, and this, you can compute with this, hopefully, in the end.
So Steve Vickers told us that we should embrace topology, right? So instead of considering the set of functions from x to y, we should always consider the formal space of functions from x to y.
Yeah.
And Alexander Oldenziel had this idea that we should take this motto really seriously, like embrace topology from the start and never talk about sets. And I have the impression that this idea is realized by your construction at the lower left blackboard, right? Because there, so what in the theory will just be a type X will actually be a topos, so a space.
Yes.
Right? So
right.
Vision is realized?
Yes, although I think for doing actual internal mathematics, we like pi types. And yes, you do get them by applying these models of the pi type theory. But I think both appear when you actually do things. So I know that Steve wants to completely get rid of pi types in the internal language. I like doing Martin-Löf type theory with my pi types and universes, so I'm not quite ready to go there. But I think you can work more in a style like Steve wants to do and not use these pi types so often once you have the option of just doing interpretations between theories instead.
Yeah. Thank you. Thank you.
Millie?
I would like to ask you limitation of this. When you speak about synthetic mathematics, I had the impression that for you synthetic mathematics is bound to toposes. In particular, I ask you toposes of sheaves. So that's why can you tell me why? And eventually, because we couldn't, why doesn't work for thinking of toposes per se and elementary toposes, or weaker notions of foundation of mathematics? Because not all, no, maybe the theory of many theories can have a completeness theorem with toposes, but not all. So in principle, a priori. So that I wonder this. And the other question is more. What is a type theory for you?
Let's take the second question offline. I'm happy to talk about that after over some red wine or something like that. Yes. The first question, I think it's an excellent question. Why do we focus so much on these particular internal languages? Is it because maybe it's because I'm biased? I learned to love Martin-Löf type theory and then univariant type theory, and I just like to use that as a language. I think it's very intuitive to think about constructions with these means of construction: sigma type, pi types, higher inductive types, co-inductive types, maybe universes. I think that's very intuitive for me, and I can think about like I'm actually just working with these things transparently. That's not how students, when they first learn type theory, that's not how they think. But once you've gotten used to it, it becomes quite intuitive. And there are other internal languages that might be just as intuitive and very useful. And so it could be about, we have a hammer, and then when we want to do internal languages, we just use that hammer and try to make everything a nail for that hammer. And it could be that for some applications, completely other styles, maybe affine logic or linear logic, are much more appropriate, and they won't fit into this framework yet. But maybe someone will come up with a way of making a synthetic mathematics of synthetic mathematics that would encompass all these other kinds of internal languages.
No, but why not for these elementary toposes that I don't know?
Elementary toposes, well, they're not very well behaved predicatively, but of course you could do a predicative version that has a hierarchy of universes, and of course when we finish the elementary theory here of the elementary synthetic mathematics, it's going to talk about something like elementary higher maybe toposes. So and maybe I mean they're most often at least for. Well, I know I didn't mention synthetic computability. We'll hear about this later in the week. Their non-Grothendieck toposes are very important. So I don't want to rule this out. It's part of my, I'm ambitious, but I'm not that ambitious yet. But I encourage someone else to think about how can we get all of this to work together. Yeah.
Okay, I think we should stop here. Let's thank Ulrik again.